Hello? Hello? Oh yeah. Hey Izza. Yeah, nothing. I'm just working on some French homework. Okay, whoa, slow down. Another physics video? When does that due? Oh. Yeah, okay, we still have time for once. Alright. And Robbie? Alright. Sweet, okay. That's a dream team. Okay, so just text me the topic and let's get started. Alright, so we actually have time for once, which is great, and our topic is tension of objects being hung by a rope on a ceiling. Alright, that's not that interesting, but I think we'll figure something out. So, any ideas? Dude, I've said this before, and I'll say it again. I am just the editor. Okay, fine. I think they really liked the flipping physics format thing from earlier. I think we could really go somewhere with that if you want to try that again.
No, you never do the same exact thing twice in a row, okay? It's not successful. You gotta keep the audience on their feet, on their toes. You wanna keep them not expecting what's gonna happen, you know? It has to be unpredictable every single time.
Okay, dude, you did not just say that recycling ideas was not successful. Did you see how much the latest James Bond movie made? Are you joking me right now?
Okay, fine. I see your point. Alright, let's go for it. But we have to step it up a notch, man. You know, like, we're getting challenged by another group. We have to keep this so funny and so entertaining.
Did you just say another group challenged us? As in, our video has to be more interesting?
Yeah, like, it's just a competition.
Okay, well in that case, you get the paint can and I'll get the paintbrushes, and I don't get paid enough for this. Like, where'd he go? Where'd he just go? Like, do any of you want me to edit your video? I'll edit your videos. This guy's a psychopath. Please, just... Okay, hear me out. Get the bucket of paint and then we'll apply a fresh coat. Just a fresh coat right across behind us.
Dude, what are you even talking about now?
Well, you said that our video just has to be more interesting, right?
Yeah, it's just a friendly competition kind of
Well
thing.
then, for our video to be more interesting than theirs, we can literally just have a video of paint drying.
Dude, whatever. Just I'll get the suit on, you get your outfits, whatever. I'm so sick of you. Oh my god.
Flippin' physics.
Good morning, class. So, how are we today?
Yeah, Mr. Pitas. Are these two still on a field trip today?
Dude, they know that there are only two of us, okay? You don't have to rub it in every single time, alright? They know that it's like just me editing you in. Just shut up, okay? Anyways, so today I will be teaching you the basic fundamentals on how to conceive this problem. Isadora's gonna come with the practice problem right after me, and then right after that, Robbie is gonna really enforce the two lessons that both of us just did by explaining common misconceptions and going over all the work.
Mr. Pitas, it kind of just sounds like they're doing all the work and you're just not doing anything at all today.
Come here, you little... So today I'm actually going to be recreating the drawing that was sent to us. Well, the one with 2 boxes and not 3 because I'm too lazy to do 3. So anyways, in one hand I have the AP US History Study Guide, aka a book we are never ever going to use in that class. In my other hand I have a comically large version of Alice's Adventures in Wonderland, again a book that I have never opened and I never will. So I'm going to be hanging these from the ceiling, this one on top because it's actually lighter, surprisingly. I'm going to be hanging this on top, this on bottom, and then we're going to comment on them and try to see how they're interacting. I can actually think this one through. I'll figure it out. Alright, let's just, okay, I'll just see where it's going to, oh my god, come on. Okay, like right here. And I'll grab the twine. So instead of using a book model, we are instead going to look at these 2 Sharpies on string. Anyways, you can see that these 2 Sharpies are attached. So this Sharpie is attached to this Sharpie by 1 strand, and this Sharpie is attached to this strand. It's 2 separate ropes, even though this looks very unconvincing. I have no idea why I did it like this, but as you can see, it actually does fray there a little bit. So, here, let's just pull it apart for now. This is one, and this is the other. So how much weight is this rope carrying? Is it feeling the weight of this pen, or both pens? Well, the top string is attached to the pink pen, so I'd have to say The pink pen only. Wait, because the blue pen is attached to the pink pen by a rope, that means the top rope is actually feeling the weight of both the pink pen and the blue pen. Correct. Now what about this strand? Does this strand being impacted by the weight of this Sharpie whatsoever, or just the blue one? Well, this time I'd have to say only the weight of the blue pen, right? Because this rope, while it's attached to both the pink pen and the blue pen, it's only really suspending the blue pen. It's suspended by the pink pen, but the pink pen isn't actually being carried by this rope at all. It's above it, not below it. Therefore, only the weight of the blue pen should be affecting the force tension for this rope. And can I go to the bathroom, actually, really quickly? Yes, a bathroom break, aka the godsend of this video, because we are going to keep having those until this gets funny. Oh, look who it is. Wow. Yeah. Hi. I am back from the field trip. Now, knowing that this rope is feeling the weight of the pink and blue Sharpie, and that this rope is only feeling the weight of the blue Sharpie, which one do you think is going to have the greater force of tension? Well, obviously, the top rope is going to have the larger force tension because it's suspending not only the blue pen, but suspending the pink and blue pen, whereas the middle rope is only suspending the blue pen. And we're actually going to be calculating force tension, I assume, by using the force gravity and adding them and subtracting them and all these shenanigans. But at the end of the day, the top rope is suspending more mass. Therefore, it is going to have the most force gravity and the larger force tension. Correct, the top one. The top one because it is supporting the most weight. So let's say in the 3-block problem, the 3 Sharpie problem, let's take a third Sharpie with some invisible string because I was not prepared and I'm ad-libbing right now. Which string would still feel the most? No matter how many objects you're adding to that strand, the top string is always going to have the biggest force tension because you're just adding more and more mass. Perfect, and which the least, assuming that there's a string connecting these two? Well, now that there's a pencil in the equation, it's always going to be the lowest item, and therefore the lowest rope, that is going to have the smallest force tension because it's only concerned with suspending the item it is immediately attached to. There's no other item underneath that you have to take into consideration. So that's probably where we're going to start our calculations, actually, starting from the bottom, because we know that the force tension on that rope is going to equal the force gravity on the item. Alright, perfect. So, we know that the string on the top is going to have the highest force tension because it is actually concerned with the mass of every single object underneath it, because it is holding all of them up to the ceiling. However, the string on the bottom is actually going to have the least force tension because I actually needed this. It is only concerned with the object that is right at the bottom, because that's the only thing it's actually holding up. That's the only thing it's actually feeling the tension of. So now that we know this, we can start making the correct calculations, which Isadora will now show in the next video. Hey, yo, man, sorry I'm late. Wait, did you guys already finish filming? Are you guys done? Did you guys start without me? Dude, we tried calling you, alright? We were gonna write you the script, but you didn't pick up our calls.
You know, there was a huge pile up on the 95. There were so many cars. I couldn't
well,
get
the next
through.
time, just tell us that you're in traffic.
That's not even the worst part. I was at Starbucks, and the barista steals all the coffee.
So I guess you're gonna have to want to say something now. So really quickly, how are we gonna calculate this? How are we gonna calculate the force tension in this rope and in this rope? Well, for the lowest string, all you have to do is calculate the force gravity of the item that is hanging, because we know that the items aren't moving, or at least we're assuming so, which means that in order to balance out the force gravity, the force tension has to match the force gravity. And then for the topmost rope, you just have to keep calculating the forces of gravity for each and every item, or each and every box, or Sharpie, or pencil, or whatever. And then, depending on whichever rope, you just have to add up all the items underneath it, because that rope has to be countering all of those forces of gravity combined, which is, of course, why the top rope has the highest force tension, because you have to add up every single force gravity of every single item that is on that rope, and all the ropes underneath it. Okay, sweet, we're good to hand this off to Izza now, I think. So, what time did she need this by? Oh, come on.
Okay, example 1. We're trying to find the tensions of the first string overall and the string attached to the 2 kilogram and the 5 kilogram. So we try to find the force of gravity acting on both the boxes. So it'd be 5 times 9.8, which is 49 newtons. And here the force of gravity is 2 times 9.8, which equals 19.6 newtons. So to find the first tension of the overall string, or the tension of the string acting on the 5 kilogram box, you do 49 newtons plus 19.6 newtons, and you get 68.6 newtons. So the first tension we found of the overall string is 68.6 newtons. And now we have to find the tension of the string acting upon the 2 kilogram. So because the gravity is 19.6 newtons, that's the force of tension on the string for only the 2 kilogram. So it's 19.6 newtons. Example 2. In this example, it is 3 boxes hanging on a string instead of 2. So we're going to find 3 separate tensions. So we're going to find the force of gravity on all 3 boxes. So we're going to do force of gravity equals 10 times 9.8, which is 98 newtons. Force of gravity on the 23 kilogram box is 23 times 9.8, which is 225.4. And then the force of gravity on the 14 kilogram box is 14 times 9.8, which is 137.2 newtons. Now we found the tensions or the forces of gravity on each of the boxes. So to find the 4 tensions, first we do tension 1, which is the overall string. We add all the forces. So that is 460.6 newtons. Then to find the second tension is the string or the forces on the 23 kilogram and the 14 kilogram. So you add the forces of the 23 and 14 kilogram boxes. So 225.4 plus 137.2, which is 362.6 newtons. And the last tension would be the force or the string acting upon the 14 kilogram. So the fourth tension would be 137.2 newtons.
Buongiorno, and welcome to Robbie Does Physics. So, my colleagues just went over how to solve problems of this type, weights hanging from the ceiling. Now, we're going to be looking at some mistakes, much like myself, that people often make when solving these sorts of problems. Let's get closer. Whiteboard, never heard of it. Paper tape to the wall, that's what the pros use. I've lost my pen. Okay, there we go. Not gonna edit that out. So, we've got our weights and we've got it from the ceiling. Gravity, 10 kilograms. 10 times 9.8 meters per second squared is 98 newtons of force pulling down this, and half of that, 49 newtons of force pulling this block towards the ground. So when it's asking for the tension force of the top rope and the tension force of the bottom rope, you've got to remember that there's an additive effect. So according to this top rope, it's not just holding 10 kilograms. It's not just 98 newtons of tension force. As far as this stupid little rope is concerned, like imagine being a rope, couldn't be me, it's actually holding 15 kilograms. So the calculation you make isn't just 98, it's 98 plus your bottom weight, which is 49, which is 147 newtons. Another thing to remember is that this bottom rope, the force pulling down on this is not added to this one. This little rope, all it knows is that this is a stationary object. So this thing, this could be the ceiling as far as just this bottom chunk of the problem is concerned. which means you don't worry about anything above it. And another thing to remember is that F net of all of this is 0. These boxes aren't flying up, down, tearing panels off of the ceiling, collapsing. There's no calamities. So since they're not moving, we know that all of these forces have to equal out. And that's why these problems are relatively quick, is the gravitational force on this box is exactly the same as the tension force at the top and bottom of this rope, because there's no normal force. Believe it or not, that's actually the end of my segment. There aren't too many mistakes to make with this because it's so freaking easy. No, I'm just kidding. It is relatively challenging in that you have to keep concentrated. Don't make mistakes with negative signs. You're also going to find that you shouldn't be getting any negative answers for tension force, although that might be a problem because if you're using negative 9.8 in your calculations, it could crop up. But that's just about it. So I will take that as a cue to leave. I actually have a visitor. There's a spider in here with me. So thank you very much for your time. If you'll excuse me. Ah!